very good evening to Doctor. And today our group would like to present on Halwa project, which the industry we chosen is in the Kenya Second Height with production chemical compound DMDS dimethyl disulfide. So before we start, I would like to introduce ourselves. Myself, Sangli Balkrishna, 196825, and my group members are Steven 195666, Pavitra 197581, Mohammed Haziq 198163, and Mohammed Haizat 198178. So let's begin with the result and discussion. So this is the consequence and effects result of different wine speed. The simulation result of dimethyl disulfide DMDS with different speed, and when the leak at 30 centimeter circular opening diameter from hole in horizontal cylindrical tight. So the figure 1, which is wine speed at 10 mph, and figure 2, wine speed at 30 mph, and the figure 3, wine speed at 50 mph. So the result are okay. So source of the leakage strength data of various wine speed based on Halwa simulation equation. So the possible occurrence involves the releases of toxic gas. So the releases period was assumed to last 5 minutes, and the estimated release amount with different wine speed was 40.1 kg, 62.5 kg, and 75 kg. So for the source of height and source of temperature and release of durations are constants. Okay, so the table 1 shows the source strength for gas releases from leakage with different wine speed. Okay, figure 1, 2, and 3 display the affected region based on Aloha estimate. All of the simulation results shows that toxic treat zone are yellow, which is between 0.5 ppm and 1000 ppm. So it can be seen that the wine speed of 10 mph gives 890 meters of treat yellow zone, wine speed of 30 mph gives 630 meters of treat yellow zone, and wine speed of 30 mph gives 531 meters of the treat yellow zone. Therefore, it can be concluded that the height of speed wine, the lower of distance treat zone. It is because the increased speed of wine will make the leaking of dimethyl disulfide relative density lower due to the increases wine speed of air that will increase the relative density of air. So next, the consequence and effect result of different type of chemicals. So the simulation results dimethyl disulfide and ethyl mercaptan with speed 50 mph, and when the leak 30 centimeters circular opening diameter from 4 in horizontal cylindrical tank. So this is the figure 4 and figure 5. For the figure 4, the dimethyl disulfide at wine speed of 50 mph, and the following the figure 5 is ethyl mercaptan at wine speed of 50 mph. So next, my friend will explain more on this.
The consequences and effect result of different type of chemical. The simulation result of the methyl disulfide and ethyl mercaptan with speed of 50 miles per hour, and when the leak is 30 cm circular open diameter from hole in horizontal cylindrical tank, shown in the figure 4 and figure 5. Assuming that atmospheric option wind direction from 50 degree, measurement height above ground is 3 meter, ground roughness is urban or forest, cloud cover is clear at temperature 30 degree and no temperature inversion, and the relative humidity is 5% when the dimethyl disulfide and ethyl mercaptan leak. The diffusion ppm of DMDS and ethyl mercaptan was divided into 3 categories, which were greater than 0.5 ppm yellow, greater than 1000 ppm orange, and the greater than 5000 ppm red. The source of the leakage strength data for different type of chemical, the methyl disulfide and ethyl mercaptan, based on the Aloha simulation equation as shown in table 2. Here, table 2. This one, table 2, the possible occurrence involved the release of toxic gases. The release period was assumed to last 5 minutes, and the estimated release amount with type of chemical was 189 kilogram, and for the methyl disulfide 75 kilogram. Seeing the leakage result in the emission of the if no combustion occur, it led to the harmful effect that might result in a fatal event. Figure 4 and figure 5 display the affected region based on the area of Aloha estimated. However, the event modeled by Aloha are flammable or area of vapor cloud and the blast area of vapor cloud. There is no potential blasting resulted from explosion in this scenario, as the LOC was never exceeded due to no part of cloud is above the LEL. It was less than 10 meters dispersion. Based on the figure 4 and figure 5, both of the methyl disulfide and ethyl mercaptan results show that the toxic zone are yellow, which is between 0.5 and 1000 ppm. The orange red zone and the red zone were not drawn because effect of near field specialist make dispersion prediction less reliable for short distance. So the software unable to draw the diffusion orange red zone and red zone. Based on the figure 4 and figure 5, it can be seen that the DMDS wind speed of 50 miles per hour gives 531 meters of yellow trade zone, and ethyl mercaptan wind speed of same give 598 meters of yellow trade zone. It is because the properties of both chemicals are different. The density of ethyl mercaptan is 0.86 at 67 meanwhile the density of the DMDS 1.06. Due to ether matter is lighter than the DMDS, the dissipation leaking of the ether receptor are greater than the MDS with the same speed of 50 miles per hour. The wind can push the lighter substance easier than the heavy substance. Thus it can be concluded the density of property is the important that will affect the dissipation of leaking substance. And next, the consequences and effect result of different size leakage. The simulation result collected by using Aloha software for our industrial facility with raw material DMDS were tested out in 3 different sizes of leakage: 50 cm, 30 cm, and 40 cm. The wind is speed constant which is 20 miles per hour at 28 degree. The type of tank is vertical cylinder tank with a mass of 2,020 kg. The leak is from the whole of the tank, which is the tank is 35% of full of its capacity. A flat of homogeneous surface is assumed and no invasion height while the humidity is 50%. The chemical escape as a liquid and form an evaporating puddle. The distribution ppm of the MDS was divided into 3 categories, which yellow, red, orange, and red. The source of the leakage strength data for various sets of leakage in Aloha simulation equation as shown in table 3. Table 3, the possible occurrence involved the release of toxic gases. The release period was assumed to last 5 minutes, and the estimated release amount with difference was 90.75 kg, 19.9 kg, and 90.95 kg. Since the leakage resulted in emission of air if no combustion occurred, it led to a harmful effect that might result in fatal event. From figure 7, 8, and 9, the display affected region was area of vapor cloud. There is no potential blasting occurred resulted from implosion in this scenario, as the LOC was never exceeded to do no part of the cloud is above the LEL, and it was less than 10 meters of dissipation. So based on figure 7, 8, and 9, all of these measures show that the toxic threat zone are yellow, which is between 0.5 ppm and 1000 ppm. The orange red zone and red red zone were not drawn because of near field patchless made dissipation prediction less reliable for short distance. Thus, the software unable to draw the diffusion orange trade zone and red trade zone. Consequences modeling was made using the Aloha software, where it refers to the calculation of estimation of numerical value or graphical representation that describe the credible physical outcome of loss. Of loss or containment scenario involving flammable explosion, explosive, and toxic matter with respect to their potential impact on people, assets, and the or safety function. The scenario of the tank was containing an unpressurized flammable liquid which led to tank failure. And based on the figure 7 and figure, all of them have the same traction distance and the time taken are the same. It calculated the different size of leakage that didn't affect too much the result, and since most of the value are more similar are the same for all the 3 sizes.
Risk evaluation on consequence and effect analysis. Based on our project, we have 3 different scenarios, which is the first one is different wind speed, the second one is different type of chemical, and the third one is the scenario different, which is the third one is the different size of leakage. So basically, as you can see here, the first scenario we have 3 different wind speed, which is 10 mph, 30 mph, and 50 mph. While the second scenario we have 2 type of chemical differently, which is the DMDS, dimethyl sulfide, and the second one is ethyl mercaptan. And lastly, we have the third scenario, which is different size of leakage, which are 15 cm, 30 cm, and 45 cm. So for the first scenario, the release rate for each of the wind speed are different, and it's the same as the mass release. They are all different for each of the wind speed. For the event, it is a toxic threat and the distance to LOC. So the consequence distance, we have 3, which is red, orange, and yellow, but both of the red and orange are nil, while the yellow for each of the wind speed are all stated in this table 4, which is a summary of the consequence and effect analysis. So this is the event frequency, which is stated in the table. So the second scenario are the same, which is the release rate for both of the type of chemical are different. Then the mass rate also the same, which is they are different, and consequence this distance is the same as I explained before, which is the red and orange are nil, because it's too small, so it's we assume it doesn't have it, and the yellow one are also different. So the third scenario, we have a size of leakage there, and then the release rate are quite significantly different there, even though there's a small little bit of different, but still the mass is also different, and it's all the same because the distance this is all stated in the table. So the Aloha software result and calculated the implication and result of the incident. So the Aloha software modeled 3 areas that were red, orange, and yellow, as I stated before. And red and orange we consider as nil because we cannot measure that. The event frequency was taken from HSE, which is Health and Safety Executive of United Kingdom. Okay, so the next one is individual risk and acceptance criteria. Based on the two scenario, all of them have the individual risk per annum frequency as stated in the table 5, which is the risk summation from all scenarios. So the overall risk outcome for individual risk per annum, IRPA, based on the identified scenario and the most likely toxic incidents. So as there are 3 zones for each Aloha model, and the only region take into account in the estimation of the total IRPA with respect to the danger associated with the 2 situations was the LOC gap in the yellow zone. So based on the figure 9 here, as you can see, the individual risk contour to NRA Kenya Operation Facility, which are located in Terengganu, and the total individual risk per annum IRPA was 1.9 times 10 power negative 3, which is the NRA Kenya operating plan. And this number surpasses the criteria for risk acceptance set by DOE, which is only 1 times 10 power negative 3 per year. So the next one, which is the societal risk. So the simplified analogy as illustrated in the study is used for measurement of societal risk as reported by CCPS 2009. So it was noted that within the building itself, which consists of workers and surrounding other facilities, the opportunity that people will be impacted within the incident implication. So based on the table 6, the total number of affected population for each predicted scenario. So we have 3 predicted scenarios here. So the estimated population for each of the scenarios that were affected by the risk, which is the societal risk, as is stated in this table, which is exceed 1,000 people here. So the affected population will be the employees inside the plant and other local workers and the resident in the community for scenario 1, 2, and 3. So the resident in scenario 1, 2, and 3 may have significant effect on anyone nearby of this area, such as a toxic release. So table 6, as I stated before, indicate the total number of affected population for each predicted scenario for 2,000 people per kilometer. Okay, so that's all from me. We will go for the next presenter. Thank you.
Hello doctor, I am Steven. Now I am going to discuss the validation of model inaccuracy and uncertainty. Using model validation, the risk can be characterized, although the model of validation sequence, or the accident sequence rather, cannot be reliably demonstrated. The collection of scenarios and the incidents used to classify their consequences, although various variables led to the precision of absolute risk outcomes. Now, there are 3 things that needs to be considered. First is risk analysis for all major contributors. Second, realization of mathematical models employed. The third is statistical uncertainty associated. From our results, table 1 to table 3 at different wind speed, we compared this to the different journal we found. That is same place, which is in Malaysia, particularly Teluk Kalong. Also, they use the Aloha simulation for this analysis. For figure 10, you can see that there is a chlorine that they used for the main component of chemical compound, which is on the Malay Sino-Chemical Industries at Teluk Kalong industrial area. Having second scenario with that, that has wind direction, wind speed, and time. Lastly is the different size of leakage, compared to the facility of Malacca Power Plant. For table 7, you can see the parameters that were set that apply to TG1 complex. Firstly is the 3 different leakage size, which is 25 mm to 203.2 mm. The wind speed and wind direction that is kept constant to 14 meters per second, and the direction was southwest to northwest. Pressure and temperature were kept constant as well through the simulation, as the only size of the leakage were kept different. Lastly, in the table 8, they conclude that different of size leakage will affect the rate release, but the value was not used or be compared to each of the size of leakage.
Next is the systematic preventive measures of hazard. In Kenya, there are 6 systematic prevention measures which can be taken. The first one is identify control options. This is to obtain coordinate and also analyze the details of staff to assess the categories of hazard. And the second one is to select controls. This is to monitor all severe hazards instantly. The third one is to develop and update a control plan. This is to track the management strategy lays out on how the chosen safeguard will be applied. And the fourth one is choose control to secure staff during non-routine procedures and emergency conditions. So the risk management strategy should be provide measure to cover staff during both non-routine procedures and also emergency conditions. Can also be known as expected emergency conditions. And number 5 is implemented selected safeguard at workplace, meaning implements risk management steps in line with objective to settle in trade control strategy. The 6th is follow up to ensure that the assessments are efficient. It is so important for the assessment to be efficient in order to ensure sufficient security. So next is the emergency response strategy. It's actually important to perform a risk evaluation to determine the possible emergency situation. So the emergency plan should be aligned with the goals of the performance. Therefore, there are 5 emergency response strategy to be considered and also to be applied. The first one is comprehensive pre-emergency planning and coordination with the third parties organization. Second one is in-depth study and design of personal rules, lines of authority, training and also communication. Third one is easy access of evacuation routes and procedures. Fourth one is decontamination process must be maintained and monitored regularly. And the last one is PPE and emergency equipment must be ready and worn at all costs. So that's all from our presentation. Thank you.